Hi, ladies and gentlemen. This is Mr. Green. This is another in my lessons on Algebra 2. We are moving on through Unit 2. We have done the first three lessons. We're in Lesson 2.04. And you know what? I get the feeling, I get the feeling every once in a while that sometimes we do math just for the sake of doing math. But in this situation, we really aren't. The whole aspect of growth curves and decay curves have some real applications and things that are outside of just the math community. Okay, so we're going to look at some real world situations: money and banking, populations of people, bacterial growth, and radioactive decay. These are all real world situations. Some of them are science related, but money in a bank? Man, I hope you all have the luxury of having that in the future, and you need to know how money grows, and this is really an important aspect. Okay, so we're going to look at, first of all, a bacterial growth problem. Bacterial growth is easy to model. You're going to use this formula right here. There's going to be some B, some constant factor in the front here, and then this is the rate of growth that you're looking at. 1 plus that rate of growth. So Suki starts a bacterial culture in her biology class. She reserves her observations for the first several hours. How many bacteria should Suzuki expect to see after 5 hours, 10 hours, 15 hours, and 24 hours? Okay? Okay, so what are we looking at here? We're looking at a bacterial growth problem. To set this problem up, what you're going to do is you're going to say y equals, you're going to have some b, some factor here in the front, b in front. You're going to say 1 plus whatever her rate of growth will be, okay, r, and then you're going to have t up here, some time. Okay, so she's wanting to know after 5 hours, 10 hours, 15 hours, and 24 hours. So what would you do? I would set up a table just like this. And some value t time goes there. And then the y, this is going to be whatever her growth is here. So you're going to set it up after 5, after 10, after 15, and after 24 hours. You would record the values that you would get in here. Okay? And having said that, once you get these values recorded, you could then go through the process of solving the problem and finding out what the B is and finding out what the rate is here. Okay? If you take this one and divide it by this one, you'll find what that rate is, because it'll tell you what the successive values, you would see what the growth is. Okay? Well, actually, you got to get it so that it's growth of 1 unit. But I mean, you can use this formula up here and figure out what that rate is. You can also figure out what the B is based upon the starting point and how much it's going to be, how faster it's going to grow. Okay? Remember, this formula falls apart after a period of time because bacteria will eat up all of its food and it won't continue to grow unlimited. Okay, so there are some limits to this formula, but this is the way you would set it up and the way you would get it going. Okay, so here's an example. In 2000, this is a population example. It says in 2000, the population of a country was 10 million something. The population is expected to grow at 8% each year. It says predict the population of the country in 2015. Well, you know what? We've got that formula. Y equals some B times 1 plus 0.08. Where did I get the 0.08? That was the rate. They told you what it was expected to grow at. T. Now, the question becomes, what do you use for T? I'm going to use the number of years, okay? I'm not going to use 2000 and something because that really is going to throw off my numbering a lot here, okay? So what I'm going to say is I'm going to say at year 1 and in the year 2000, which is my year t 0. That's year 0. Okay? What is the value of y at that point? Well, it was 10,234,700 or 678, and we're wanting to know the year 2015. Well, that's going to be year 15, isn't it? So we can use this information right here, this one point, to help us solve this equation. We've got y. Well, you know what y is going to be? It's going to be that 10,234,678 is equal to b, some value here, times 1.08 to the 0th power. Well, something raised to the 0th power is 1, so that means my b is going to be this 10 million number over here. Can I find what it would be at year 15? Sure. It's going to be y is equal to 10,234,678 times 1.08 to the 15th power. Wow, large number. Let's go back to our calculator here and do a little bit of calculation with that. So we've got 10,234,678 times 1.08 raised to the 15th power. And you do that and you get that number right there, which is 32,466,129. 129. Lots and lots of people in 15 years. Okay? So they're asking, in what year will it first exceed 12 million people? Whoops, didn't write that right. 466. Yeah, 32,466,129. So the next question there is, when will it first exceed 12 million? You know what? I think the easy thing to do here is to press y equals. Clear this one out. Put the formula in here. 10,234,000. 34,678. Make certain I got it in the right. 10,234,678 times 1.08, and then raise that to the x power. Okay? Press enter. Graph it out. You won't see anything on the graph. Press second graph. Yeah, you won't see anything on it because it's just so out of bounds. It's ridiculous. So second graph. And you see here at 0, we're at that 10, 200 and some odd number. It's e to the 7th. That's about what we're looking at, right? And if you go down the graph here to 15, you would see that we were at 32,500 something. Well, that's what we have here is 32,500 something. 500,000. So, I mean, it shows you the number, but that it's not as good because it's putting it in scientific notation. But the question B there said, when did we first exceed 12 million? We can see it right there at that point right there, 12 million. So that's at year 3. Okay? And you can see how I worked through that problem. Finding the B, How did I find the b? Well, I used this value right here as the b, but I worked it out. I used the 0th power for the year. That made that equal 1. That made the b equal to the value that I had at that year. That's what makes this problem easy to do. If you did it with the year 2000 sitting in there, it's not easy to do, and you get very different answers, okay? So you got to know how to work these type of problems. Okay, let's look at decay problems just for a second here. If I were looking at some sort of a decay problem, like the sales of a popular doll, it's decreasing, okay? It decreased from 2000 to 2005. If the decrease in sales continues at this rate, what will the sales be for 2010 and 2020? I'm going to do a similar type thing here. I'm going to make this year 0. That would make this year 5, right? That's going to make this year 10 and this year 20. I'm going to use the same type of formula. Y equals, if I make this year 0, my B is going to be the same value as that sales there. 1496, 330. And what we're looking for is the R. 1 minus R to the teeth power. Right? Well, you know what? What we can do is we can say, well, this was actually 1 year later. This one's actually 5 years later. Let's look at what 1 minus R to the 5th would be. Well, do we have to? We know what that value is going to be. It's 1158037 is equal to 1496330. 1 minus R to the teeth power. So I can actually divide by this one, right? 1496330. And that's going to be equal to 1 minus R to the teeth power. I can take the teeth root, teeth root, and I will have 1 minus R equal to that teeth root. So I'm going to do that. I'm going to do all this on the calculator rather than showing it to you on the screen there. Okay. So I'm going to take up just a little bit. Thank you. Clear this out. Thank you. Clear that out. So I'm going to have 1158037 divided by 1496330. And what do I get when I divide those out? I get 0.7739. Okay? Well, we were looking at the 5th here, 5th year. So I'm going to raise that to the 1/5 power, dividing it by 1/5. Okay? That's the 1/5 power. And when I raise that to the 1/5, I get 0.95. See all these zeros here? This is probably going to be rounding out here. But that is going to be what I'm looking for, 0.95. 1 minus the rate is 0.95. That's what I was looking for. So 1 minus R is equal to 0.95. What does that make R? That makes R 0.05. How did I get that? Well, subtract 1 from both sides, you get negative 0.05. It's equal to negative R. It's divided by -1. So my R is 0.05. So what can I do? Come back up here to this original equation. Replace this R with 0.05. Go back over to my calculator. Press Y equals. Clear that out. Key the number in. 1496330 times parenthesis 0.95. What did I do? 1 minus 0.05, 0.95. Raised to the teeth power. That's all I have to do. Press enter. Now I can do a graph. You won't see much here because it's way off the screen. And waiting for the little lines to disappear there. Second graph. Now, If I look at year 1, 1.42. Right? And if I look at year 0, 1.5, that's what we had there. If I look at year 5, 1.16, is that what we had there? 1.1, yeah, pretty much 1.16. So can I look at year 10? Sure, let's go down here and look at year 10. At year 10, we're looking at 895,908. Wow. Okay. Let's look at year 20. At year 20, we're looking at 536,413. I think we found the values that we were looking for, didn't we? We found those values right there on the calculator. That's what you can do to find a decay problem like this. Now, radioactive decay is a little bit different. Radioactive decay is radioactive material has what they call a half-life. And this is coming from science, not from math. Half-life. Half-life is the amount of time it takes for 1/2 of the substance to decay and be gone. So what do they use for their R in that situation? They use 1/2. So 1 minus 1/2 is 1/2. Okay? And this T, they're also dividing it by H. H is the time that it takes to get to that half-life. So what are you looking for in T? Well, T is the amount of time that you're going. H is the amount of the length for the half-life. So if they say it takes 10 years to get to that half-life, that's what you're going to use for the H here. Okay? So you're going to say B is the amount of substance that you got. You're going to say 1/2. T is the number of years that you're looking to look at, and T is the fact that it took 10 years to get to a half-life. So if they wanted to know how much would we have left after 3 years, you could say 3 divided by 10 to get that exponent. Does that make sense? So what are we looking at here? Carbon-14 has a half-life of 5,730. H equals 5,730. Archaeologists find bone material from what appears to be a human leg. One of the archaeologists thinks the leg is 10,000 years old. Okay? 10,000 years old. They're thinking that T is equal to 10,000 years. Okay? What percentage of normal carbon-14 levels should she expect to find in the leg? Okay? So, this is really easy to do. They're actually looking for what value of B that they would have here. Okay? So what you could say is we've got one whole leg, and that's equal to B, which is what we're going to be looking for, times 1/2 of 5,730 divided by 10,000. Okay? Well, first of all, we can do this on the calculator and not have to do just a whole lot of work for it. Because, after all, this type of mathematics, when we get to the point, I know people are going, calculators are evil in some situations. They are. But when you're having to do this higher order math, if you understand the math, the mechanics of it are not what we're worried about. Okay? So, I want to show you that 5,730 divided by 10,000 is 0.573. So if I take 1 raised to the 0.573 power, what do I get? I still get 1. Stop. Stop, 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 stop. Okay. Okay. I wrote them down correctly here. H is this, T is this, and then reversed them there. I'm sorry. 10,000 divided by 5730. It helps when you do your thinking online. No, never helps. Okay, so here we go. We're looking at 1/2. Well, that's 0.5 raised to parenthesis 10,000 divided by 5730. And what do we get? 0.2982. So look at what we've got here. We've got 0.2982. That's really telling you 29.82% of whatever bone they've got right now will be equal to, of the original bone, will be what bone you've got right now. This is the percentage that they're looking for in that situation. That's what they're wanting to know right there. It doesn't matter how much bone we've got right now, okay? We don't know how much it is. We can just assume that those are going to cancel each other out because of this percentage, okay? That's what we're looking for, is that 29.82%, about 30%, okay? So, compound interest, this is what I was wanting to get to. It says compound interest is a good way to earn money. So when we're looking at compound interest, we're looking at the P, which is the amount of money that you put into the bank to begin with, that's the principal, is equal to 1 plus R divided by N. R is the rate that you're getting in your interest. N is the number of periods that you do per year. And you're multiplying that times NT. Or you're raising that to the power of NT. N is the number of periods per year. T is the number of years. Okay? So this A is the amount of money that you will have at the end of however many years. So this one down here says, find the total amount of money after 2 years of an investment of $15,000 in an account paying 4% interest. So I'm going to say that A is going to be equal to, and we're compounding it annually, right? It's going to be equal to $1,500, $1,500 times 1 plus 0.04 divided by 1, because we're compounding it annually, right? Number times per year, once per year. 1 times, how many years? 2. That's easy enough to work out on a calculator. This other one over here, quarterly, A, will be equal to 1,500 times 1 plus 0.04 divided by 4, quarterly means 4 times per year, raised to the 4 times 2. So, my question to you is, which one do you think is going to be more? Let's look at this. Let's actually try to work these out on the calculator and see which one would be more. Just to show you what's going on here. 1,500 times, parenthesis, 1 plus 0.04 divided by 1, parenthesis. I'm just making certain I get everything in here. Raised to the 1 times 2 power. Enter. Well, after 1 year of this, or 2 years of this, it's at $1,622, compounding it annually. If we do the same thing, 1,500 times 1 plus parenthesis 0.04 divided by 4, parenthesis, raised to the parenthesis 4 times 2, parenthesis, power. What do we get when we do that? 1,683.84. You can ignore anything after the second decimal because we're dealing in dollars and cents here, right? They were never going to round up on a bank. So which one gave you more? This one was $1,683. This one over here was $1,622. Now, we're talking a difference of $61 here. But the whole point is, you didn't do anything different. You either put the money in this bank or you put the money in that bank, and in this one you made $61 more. Does that make sense? Sure. And it's a difference of knowing whether they're compounding it quarterly or they're compounding it annually with the same interest rate. No differences there at all. Okay? Okay, moving forward. I do appreciate you all making certain you let me know that you're in Algebra 2 when you're sending me questions via K-mail or sending me instant messages. It really does help. I look forward to seeing you in the next class connect or in tutoring. Tuesday, Wednesday, or Thursday. I'm there to answer your questions. Talk to you later.